In the previous video, we showed that reversible cooperative binding of protein X to enzyme is described by a Hill function. In this video, we show how Hill functions provide an opportunity for bistability. We showed that reversible cooperative binding of protein X to enzyme is described by a Hill function. Suppose that this enzyme in its tightly bound conformation can catalyze the conversion of a protein W to protein X. In this cartoon, tightly binding the 4 copies of protein X by compression of the enzyme's spine has pulled open the jaws of the catalytic site. The portion of the time rate of change in the number of copies of protein X owing specifically to catalysis is equal to the product of the rate of change of X with respect to the number RC of catalysis reactions elapsed since some reference time, multiplied against the time rate of catalysis events. Each catalysis event produces an addition to the number of copies of protein X. According to the law of mass action, the time rate of catalysis events is equal to a proportionality coefficient, here called beta, multiplied by the number of proteins W available to be converted, multiplied by the number of bound enzymes, which is itself the total enzyme population multiplied by the bound fraction F sub b. The bound fraction is described using the Hill function already on this slide. If we consider the situation in which the protein W is available in abundance, meaning never appreciably consumed, and if we assume that the total number of copies of enzyme is maintained, then beta times W times E sub tot can be replaced by a constant that we will call beta twiddle. Suppose in addition that protein X can degrade. The portion of the time rate of change of protein X owing specifically to degradation is equal to a product. One factor is the change in the number of copies of protein X owing to each degradation reaction, where R sub d is the number of degradation events that have proceeded since some reference time. Another factor is the time rate of degradation events. As a consequence of each degradation, one copy of protein X is lost. According to the law of mass action, the time rate of degradation events is proportional to X. The total time rate of change of the number of copies of protein X is a sum of the partial rates of change owing to catalysis and degradation, which can be copied from above and moved to the top right corner. We will individually plot the pieces of this expression for dx dt with respect to X. The white question mark indicates that we will use this set of axes for 2 plots, one plot for the partial rate of change in numbers of copies of protein X owing to catalysis, and the second plot for the partial rate of change owing to degradation. The Hill function associated with catalysis, highlighted in a red box, corresponds to the red sigmoidal curve. This curve saturates at a maximum height of beta twiddle. The linear term highlighted in the blue box corresponds to degradation. The leading negative sign is deliberately omitted from the blue box, so the corresponding blue line is plotted taking on non-negative values. In this example, beta twiddle and alpha are chosen so that the red catalysis curve intersects the blue degradation curve in 3 places. These are the locations where catalysis and degradation are balanced. In other words, where the total rate of change dx dt is 0. The total rate of change is negative where the red curve falls below the blue curve. Protein in net is being lost when degradation is faster than production. Dx dt is positive for concentrations of X where the red catalysis curve is above the blue degradation curve. Protein in net is being accumulated when production is faster than degradation. Vertically orient the protein concentration axis and use horizontal quivers to indicate the points at which dx dt equals 0. These are the values of X where time courses of protein abundance X versus T must be flat. In this region, dx dt is negative. The slopes point downward. In this region, dx dt is positive. Slopes point upward. In this region, dx dt is again negative, and slopes again point downward. Because the expression for dx dt depends only on the concentration x and not on the time t, the same arrows can be copied and pasted onto all other times, filling out this direction field. Tracing out plots of x versus t consistent with this field, we see that the top and bottom steady states are stable. Concentrations of protein X deviating slightly from these steady states are attracted toward them. The steady state in the middle is unstable. Even curves that are initially near this steady state are repelled away, eventually approaching one of the other steady states. This is bistability. In this slide deck, we've motivated the law of mass action, used the law of mass action to describe cooperative binding with Hill functions, and then shown that cooperative binding can generate bistability. If you discover that an enzyme binds seemingly redundant copies of the same protein, you can ask whether a thresholding effect, or bistability, has downstream consequences in your system. Similarly, if you notice that a biological circuit you are studying exhibits a threshold effect rather than a graded dose-dependent response, you can ask whether molecular components in your system can be analyzed by applying an understanding of cooperative binding.